E equals mc². You've seen it 1,000 times, but can you actually derive it? In the next 5 minutes, we'll start with one fact, that light travels at the same speed for everyone. From there, we'll discover time dilation, then relativistic momentum, and finally prove that mass is energy. Here's how. This is our starting point. Light travels at exactly c, about 300 million meters per second, not relative to anything in particular, just c. Think about two cars driving toward each other. If each is going 50 miles per hour, you would measure the other approaching at 100. You just add the speeds. Now imagine you're flying toward a light beam. You're moving at velocity v. Classical physics has a clear prediction. The light should appear faster. You'd measure c plus v. But when physicists actually tested this, they found something strange. No matter how fast you moved toward the light, away from it, sideways, you always measured exactly c. The speed of light doesn't care how you're moving. It's the same for everyone. Einstein realized this wasn't a measurement error. It was a clue. If the speed of light is truly constant, then something else must be changing. He discovered that it is space and time that change. Einstein built his theory on two simple postulates. First, the laws of physics are the same in all inertial reference frames. No experiment can tell you if you're moving uniformly or standing still. If you're in a sealed lab moving at constant velocity, there's no way to detect that motion. Second, the speed of light is the same for all observers. It doesn't matter if you're moving toward the light or away from it. You always measure exactly c. These two statements sound innocent enough, but together they force us to abandon absolute time. Let's work out what these postulates imply. Consider a light clock, a beam of light bouncing between two mirrors. When the clock is at rest, light travels straight up and down. The time for one bounce is just the distance divided by c. Now, this clock is moving sideways. From your perspective, the light travels a diagonal path. It has to cover more distance, but it still travels at exactly c. We can use the Pythagorean theorem here. The diagonal distance squared equals the vertical distance squared plus the horizontal distance squared. Solving this gives us the time dilation factor. Moving clocks tick slower by a factor of gamma. This factor gamma appears everywhere in relativity. Let's see what it looks like. Gamma equals 1 divided by the square root of 1 minus v squared over c squared. At everyday speeds, gamma is essentially 1. When you walk or drive, time dilation is completely negligible. But as you approach the speed of light, gamma grows dramatically. At 90% of c, gamma is about 2.3. At 99%, it's over 7. As v approaches c, gamma shoots toward infinity. This is why nothing with mass can reach the speed of light. We've seen how gamma changes time, but there's a second consequence. Think about it this way. Speed equals distance divided by time. Now, the speed of light is the same for everyone. That's our starting postulate. So if time stretches by gamma and speed stays fixed, then distance has to shrink. Here's what that looks like. Say a star is 4 light years away, and you're traveling at 80% of c. At that speed, gamma is about 1.67. So, from your perspective, that 4 light-year distance contracts down to just 2.4 light years. This is length contraction. The measured length equals the rest length divided by gamma. The faster you move, the shorter distances become along your direction of travel, and that connects directly to momentum in our next step. We've seen gamma change time and shrink distances. The next thing it changes is momentum. In everyday physics, momentum is just mass times velocity. The faster something moves, the more momentum it carries. But we've shown that time and distance both depend on your frame of reference, so velocity looks different to different observers. And if you use The old formula, momentum isn't conserved across frames. That's a serious problem because conservation of momentum is one of the deepest principles in physics. The fix is the same factor we've been using all along, multiplied by gamma. Relativistic momentum equals gamma times momentum times velocity. At low speeds, gamma is close to 1, so this just returns the classical formula. But as speed climbs, gamma grows and momentum increases much faster than you'd expect. Watch what happens as velocity approaches c. Momentum doesn't just climb, it shoots toward infinity. That means you'd need infinite force to push anything with mass to the speed of light. It simply can't be done. Now we have relativistic momentum. The next question is what it tells us about energy. We've got relativistic momentum, and now it's time to find the energy. We'll do it through work. When you push something, you do work on it, and that work becomes kinetic energy. The harder you push and the farther it moves, the more energy you transfer. Now, force is just how fast momentum is changing. So when we write out the work, force times a small distance, we can swap in that definition of force. And notice, distance over time is just velocity. So the whole thing simplifies. A small change in energy equals velocity times a small change in momentum. Now, we need to add up all those tiny energy changes by integrating. We plug in the relativistic momentum from the last scene. The gamma factor threads through the entire calculation, and when you work it all out, the total energy of a moving object is gamma times m times c squared. That c squared factor is what makes the number so enormous. Now let's see what happens when the object is completely at rest. Remember what gamma looks like? It has velocity squared in the denominator under a square root. When velocity is 0, that fraction vanishes and gamma just becomes 1. The object is perfectly still and you'd expect 0 energy. Wrong. When we put gamma equals 1 back into our total energy, the gamma drops away, and we're left with just mass times c squared. Even at rest, there's energy, an amount equal to mass times the speed of light squared. Just by existing, matter contains energy. Think about what that means. A kilogram of anything, water, rock, your coffee cup, contains the same energy as a massive nuclear explosion. All that energy is locked inside, frozen in the form of mass. This is what nuclear reactions tap into. When atoms fuse or split, a tiny bit of mass converts to a tremendous amount of energy. We started with one fact, that light travels at the same speed for everyone. From that single truth, we derived time dilation, length contraction, relativistic momentum, and now this, the most famous equation in physics. Mass is energy, and energy is mass. They're the same thing, measured in different units. For more science and technology videos, please consider subscribing to our channel and follow us on Patreon for early access to videos and other perks. Thank you for watching. See you next time.